This particular lecture is for semester 4 and it's related to Schrodinger equation. Okay, so first we'll discuss about time independent. Okay, Schrodinger equation. So this will be time independent. Now what we know is that to explain the dual nature of matter, Schrodinger consider every material particle to be equivalent to a wave packet, and that wave packet moves with a certain group velocity, and each individual wave which comprises a wave packet moves with a certain phase velocity. So the concept of wave packet demanded the existence of a certain guiding wave, right? So the equation of this guiding wave was derived by Schrodinger and is of immense use in the problem concerned with almost all the domains of physics as well as chemistry. So this was the basic introduction related to the Schrodinger equation. Now we'll start deriving this thing. Okay, the Schrodinger equation. So we know that a moving particle has a wave associated with it, and its nature in terms of a periodic displacement in space and time. It should be represented by a definite wave equation. Now to obtain this equation, we will consider a system of Schrodinger rather stationary waves to be associated with particle. Now if the position coordinate of a particle let x, y and z, this is the position coordinate x, y, z, and psi be the periodic displacement, okay, for the matter wave waves at any time, at any instant t. Okay, psi, this is psi. Okay, we can write a differential equation of the motion of wave as follows. That is del square psi by del x square plus del square psi by del y square plus del square psi by del z square minus 1 by u square del square psi by del t square equal to 0, where u is the wave velocity. Okay, wave velocity of particle, and psi, this psi, which is a function of x comma y comma z and t, is called the wave function, Okay, now it can be expressed as a periodic displacement and form the solution of the equation. Let this be equation number 1. So we can express the solution of this particular equation as psi as a function of x comma y comma z comma t equal to psi naught x comma y comma z comma rather into e to the power minus I omega t. So this will be equation number 2, where psi naught is the amplitude of the particle wave at the point x, y and z, and it is independent of t. So equation 2 can also be expressed, psi as a function of r comma t, where r is a vector, is equal to psi naught as a function of r e to the power minus I omega t. So if we differentiate equation number 3, okay, with respect to time, what we will get is like, you need to differentiate this with respect to time. So we'll get del square psi, double differentiation rather, del square psi by del t square is equal to I square omega square psi naught e to the power minus I omega t, which is equal to obviously minus omega square psi naught e to the power minus I omega t, or it can be written as del square psi by del t square equal to minus omega square psi. So this will be equation number 4. Now substituting this value of del square psi by del t square in equation number 1, we'll get del square psi by del x square plus del square psi by del square psi by del z square plus omega square u square psi equal to 0. So this will be equation number 5. Now here omega may be written as 2 pi nu, which is equal to obviously 2 pi, okay, u by lambda, so that omega by u will be equal to 2 pi by lambda. So this will be equation number 6. So from 5 and 6 we get del square psi by del x square plus del square psi by del y square plus del square psi by del z square plus 4 pi square lambda square psi is equal to 0, or it can be written as del square psi plus 4 pi square by lambda square psi equal to 0. So this will be equation number 7. Okay, now from de Broglie equations we have lambda is equal to h by mv. Okay, lambda equal to h by mv. So using this relation, equation number 7, the previous equation, will get del square psi plus 4 pi square m square v square by h square psi equal to 0, or del square psi plus m square v square by h cross square psi equal to 0. Here we know that h cross is equal to h by 2 pi. Therefore, del square psi, okay, plus p square by h cross square psi equal to 0, since here p is equal to mv. Now the kinetic energy of the particle in terms of the total energy E and the potential energy V can be written as half mv square is equal to capital E minus V, or mv square equal to twice of E minus V, or m square v square is equal to twice of 2m into E minus V. Okay, so substituting this in equation number, we have one more equation here. This one is equation number 8. Okay, so substituting this value in equation number 8, we have del square psi plus 2m by h cross into E minus V into psi equal to 0. So this will be equation number 9. So this is the time independent Schrodinger equation, in its generally used form. This is time independent, okay, this is the time independent Schrodinger equation. Okay, now to obtain a time dependent Schrodinger equation, okay, we eliminate this total energy E over here from time independent Schrodinger equation. Okay, so what we'll do like this, we'll just differentiate equation number 2. We have earlier derived equation number 2, that is this one, okay, which we have done earlier. We'll just differentiate this with respect to time. So we'll have del psi by del t equal to minus I omega, okay, psi naught e to the power minus I omega t equal to I minus I omega psi. So we'll have minus 2 pi I nu into psi, okay, since omega is equal to 2 pi nu. Now this del psi by del t is equal to minus I into E by h cross into psi, or E psi is equal to minus h cross by I del psi by del t equal to I h cross del psi by del t. We'll just multiply with I, the numerator and denominator, we'll get this one. Now this will be equation number, say, 10. Now we'll substitute this value in equation number 9. In the place of E psi, we'll get del square psi plus 2m by h cross square I h cross, okay, del psi by del t minus v psi equal to 0, okay, or h cross square by 2m del square psi plus I h cross del square psi, okay, minus v psi equal to 0, or arranging it, IH cross del psi by del t is equal to minus h cross square by 2m del square plus v into psi. So this is our time dependent Schrodinger equation. Okay, and in place of this you can substitute h, capital H, which is the Hamiltonian. Okay, so we'll write IH cross del psi by del t equal to h psi. Here h is the Hamiltonian. Okay, which is given by h is equal to minus h cross square by 2m del square plus v. This is our h. So in the place of this we'll write, and we'll get this particular equation, IH cross del psi by del t is equal to h cross psi. So this is our time dependent Schrodinger equation. Okay, so in the form of Hamiltonian. So this is all about the time dependent and independent Schrodinger equation. The next lecture we will discuss further the application of these equations. Thank you.